Hello, Honors Geometry students, and welcome back. Thank you so much for joining me for this circles quiz review for your upcoming quiz. So throughout this video, we are going to be going through the skills and objectives that you have learned about circles and just some key pieces of it and summaries, as well as some examples. You guys have access to this PowerPoint if you want to have it pulled up or printed out if possible, or you can, of course, just follow along. So I want to start off with what is actually on this quiz, right? Maybe you can think of some things that we've covered. We started off, we talked about circles vocabulary and some terms. And so there was a video that maybe you can go back and find all about the introduction to like the new vocabulary. And some of it wasn't necessarily new. And so that was where we started. We then dove into one specific term, which was tangents. Right, and we really looked at tangent and even on a grid, right? And we tied in some things with algebra so that we weren't losing some of those skills about like writing equations and analyzing those equations and finding the relationships between lines. We then added on to that, right? Still talking about circles, but we looked specifically at central and inscribed angles and the relationship that those have with the arcs that they intersect. From there, we've learned about radians the last few class periods, right? A different way of measuring and a way of measuring an angle that actually gives us a lot more information and to be honest, makes our lives easier, right? And then finally, we did some work with arc length. And we didn't really do a ton with arc length. We kind of just scratched the surface, but we did that. It was our last objective that we covered. So I want to start off and talk about circles vocabulary. I thought this was cute, so I wanted to show you guys this picture. It's actually something that we used to be able to do when we were in person, but you'll get some of these fun activities next year in Algebra 2 when you're back in person and you can interact with some fun manipulatives, right? But you saw pictures like this, and if you Google stuff like this, you would see it where you're actually just labeling parts of a circle, right, with this key vocabulary that we've talked about. So some of the words were center, not a new word to us, right? The radius, also not a new word to us, and diameter, right? Those three are things that we likely already knew before this unit, right? The diameter is twice the radius. Then we talked about major arc and minor arc, and I would guess that those may have been a little bit new. The word arc, we could probably use some context clues. Well, what's the difference between a major arc and a minor arc? A major arc is greater than, there's that symbol, 180 degrees, and a minor arc is less than 180 degrees. If it's equal to 180 degrees, it's what we know as a semicircle. Right? And some things that we do want to remember about this is that if you are dealing with a major arc, that means that when we name that arc, there's going to be 3 letters. Right? So for instance, maybe I would have arc ABC. If I see that, it indicates to me that it's a major arc. If it's a minor arc, it's going to have 2 letters, just its 2 ends. Right? A and C are going to be its ends, but B, it's telling you like which direction around the circle am I going. I might just be looking at AC. So for instance, if I have a circle, and I'll put some points around this. Well, the major arc, ABC, I have to go from A. Oh, I called 2 of them C. What am I doing? Having some trouble, guys. Call that E. Where'd the point go? Okay, so I'm going to go from A. Well, I've got to go clockwise because I have to pass through B and then get to C. That's my major arc. What about my minor arc? Minor arc AC. Well, I'm not going to go to B. I'm going to go directly from A to C. You might be like, but can't I call that AEC? No, it's not necessary. If it is a minor arc, if it's less than half a circle, if it's less than a semicircle, 180 degrees, you are naming it by just its ends. Okay? We talked a little bit about a chord, right? An example of a chord is a diameter. A chord is just a segment that has its endpoints on the circle. We talked a little bit about a secant. These were not as big of things to us, and they're not things that we're going to harp on right now. A secant is a line that passes through the circle. Right? A chord stops, a secant can't stop. It has its word, that word can't. Okay? And then we did talk about a tangent, and that's an important one for us to make sure that we are chatting about. So a tangent has only one point on the circle and never goes inside it. Right? Like this is a tangent. If I were to connect the radius, those are going to form a right angle. Right? This point right here, maybe you remember, is called the point of tangency. We dove a lot deeper into this specific word after, and so we're going to do that again right now. Okay, so then we got into tangents. And the tangent theorem that we focused on was that a tangent and a radius are perpendicular at the point of tangency. Right? And that word perpendicular means that it forms a 90-degree angle. And we didn't go around assuming, we had specific ways that we could actually figure that out. Were we dealing with something on a grid? If we were, we looked at slope. And hopefully you remember that the slopes were opposite reciprocals. The slopes weren't perpendicular. That's not possible. The slopes were what we call opposite reciprocals. So we can analyze the slope, and we'll do that with this picture in a moment. If we were off a grid, we went back to our old friend, the Pythagorean theorem, right? Where a squared plus b squared equals c squared. If it didn't, if a squared plus b squared doesn't equal c squared, not perpendicular, not a tangent, right? So let's take a look at this example that I have right here. I can see my circle. I can see the center of my circle. And you know what? While I'm at it, let me just draw in my radius. And I can see this point. And I didn't give you a prompt, but I'm going to tell you the prompt. I want to draw a tangent through the point 83, and then I want to write the equation. Whoa. Okay? So I'm going to draw, and I need you to remember something really important here. If we're going to draw a line, we need 2 points. That's non-negotiable. Okay? So, well, we're on a grid. So I'm in this land. So I need to use slope. So let's see. It's going to be perpendicular to the radius. Let's find the slope of the radius. 1, 2, 3. 1, 2, 3, 4. Right? So the slope of this is 3/4. Well, the perpendicular slope to that, opposite reciprocal, is going to be -4/3. So I already have 1 point. Well, let's use this point to find another point. Let's go down 4. 1, 2, 3, 4, and write 3. 1, 2, 3. I have 1 point. I have 2 points. I've got my line. Maybe I want another point. Maybe I'm like, oof, this isn't going so well for me. I could go up 4, and then left 3. I don't know. I'm more eyeballing that one because it's off the grid, but maybe it'll help me graph it a little bit, right? So I just constructed this. I know it's a little wavy in there. So that is a 90-degree angle. And I've got 2 points. I got the point 11, -1, and 8, 3. Okay, so I did this first part. I drew the tangent. Now I need to write the equation. I have absolutely no idea what this y-intercept is. Could I find it? Sure. Do I need to? No. right? I'm going to say y equals, I know the slope, I already got it, -4/3 x, I'm just going to go ahead and use this point, -8 plus 3. There's my equation. I know some of you guys like to do it this way and just say 3 equals to -4/3 times 8 plus b and then solve for b. That's fine. It's maybe not going to be as nice, right? Like if I did, I'm going to get some crazy decimal there. -32/3 plus b, and then I have to add -32/3, which is a decimal. I'm sorry, I would have to add 3 plus 32/3, which is going to give me 41/3. Or what is that? 13 2/3. So if you like really want to do that, I feel like I've seen some of you guys do that. That's fine. But I don't want to get a decimal and round it. And my calculator is saying 13.666666666, and then it ends with a 7 because my calculator is rounding it. And you want to be exact. Nobody wants somebody to. We want precision here. Okay. Awesome. So then we went into central and inscribed angles. A central angle, we know right, like the first step is identifying, is it central or is it inscribed, or is it none of them, because then we don't have the knowledge base to deal with that right now. So if it's central, I know that it's central because the vertex is at the center of the circle, the vertex of that angle. The measure of a central angle is equal to the arc it intercepts. An inscribed angle, we can identify that by saying that the vertex is on the circle. Oh wait, sorry, on the circle, the circumference of it. That shouldn't have an S. The measure of an inscribed angle is 1/2, so equal, the measure of its intercepted arc. Remember, and we talked a little bit about intercepted arcs. Think about it like if I were to cut that angle out, it's the arc that's coming with me. It's the arc I'm going to take. Like if something's intercepted, I now have it, right? So if my angle intercepts an arc, if I literally cut that angle out of the circle, the arc that stays with it was the one that was intercepted, like it stole it. Okay, so a central angle, here's an example. 84 degrees. Oh, this arc would be 84 degrees. Hey, I've got a question for you guys. What would this major arc be? I could ask that by saying, what's the measure of arc ACB? 360 minus 84, right? I don't know if I can do that. What's 360 minus 84? 276 degrees. Here's an inscribed angle. Ooh, there's two, right? But they're both inscribed. I can see the vertex is on the circle. So if I were to literally cut this angle out, the arc that's going to come with me is DC. Okay, so the angle is half the arc. So 45 times 2 is going to give me 90 degrees. Isn't that interesting? So if I were to draw in a central angle, this angle would be 90 degrees. Then I've got this angle. If I were to cut this one out, AB is going to come with me. The angle is half the arc. Well, here I know the arc. So I've got to do 76 divided by 2. So that's going to give me 38 degrees for that angle right there. So the measure of angle ADB is 38 degrees. The measure of arc DC is 90 degrees. Okay. Let's look at another practice. What if my goal was to figure out what X is? Okay. Well, let's start with this. Where that X is what we know is an inscribed angle because the vertex is on the circle. Okay. This 31-degree angle is also inscribed. What's hard is, I guess I don't really, I guess if I extend it here, I can see where it ends, but I don't know what that really does for me, right? Like maybe that helps me. Maybe, right? Like maybe I can do 31 times 2 to get this arc right here. And I would get, what, 62? And then that's a diameter, so maybe then I do 180 minus 62, and I get, what's that? I guess this works. 180 minus 62. This wasn't my intention, but I just thought of it. 118. That's this arc. BC. Well, can you see what angle would take that with it? Oh, my inscribed angle where the X is. So shouldn't I just be doing 118 divided by 2? Yeah, what's that? 59 degrees. Interesting. Can anyone see a different way I could have done that? Another way, and this was actually when I put this problem on here, I thought of doing it. These two are the same. Why? Oh, they're both radii. So maybe you can see that BOC is actually an isosceles triangle. So this would also be 31. So I could do 31 plus 31 gives me 62. 180 minus 62. Look, I'm basically doing the same thing. I get 118. So this angle is 118. It's a central angle. So then this is 118. Oh, I'm still going to divide it by 2 and get 59. It's just a different pathway to that same answer. Maybe you even see another way. Let's do one more. Let's clear this out. I'm going to clear my drawing. Let's check this one out. Okay. So here, a little more algebra is involved. Okay. So again, oh, wow, I think I see this angle. And if I were to cut it out, this arc's going to come with it. Okay. Now let's see what happened again. And then I see I've got information about this inscribed angle. And if I were to cut it out, oh my goodness, that same arc is going to come with me. So what does that mean? I have two inscribed angles intercepting the same arc. Well, those angles must be equal. 4x plus 6 must equal to 5x minus 6. Add 6, I get 12. 4x plus 12 equals 5x. Minus 4x, I get 12 equals x. You know what? Let's go ahead and let's try to find that arc. So let's go ahead and plug that back in. Does it matter which one I plug it into? Do I have to plug it into both? No, right? But that's actually a pretty good way to check my work. So if I do 4 times 12 plus 6, I get 54. And if I do 5 times 12 minus 6, I also get 54, which should kind of make sense, right? 5 times 12 and 4 times 12, they're going to be 12 apart. I'm adding an extra 12 in there. So if I add 6 to one and subtract 6 from the other, I'm going to end up in the same spot, which is kind of neat, right? So I get 54 degrees for both of these inscribed angles. So then what is the measure of the arc they intercept? The inscribed angle is half the arc it intercepts. So let's double it, and I get 108 degrees for that arc. Okay? So lots of good practice with this. Okay, so then we got into radians. I forgot to make this animate. Sorry, guys. 1 radian is 1 radius length around the circumference of a circle. 1 radian. So if I take this radius and I just lay it around the circle, the measure of that is 1 radian. Right? It's a lot less arbitrary than like 1 degree. Like somebody had to be like, this is 1 degree. Whereas a radian is a radius length. Regardless of how big or small that circle is, it's going to happen proportionally. All circles are similar. Right? So an entire circle is 2 pi radians. Right? It was about 6 radius lengths fit, so 2 pi radians. Meaning 180 degrees is pi radians. And this is really the basis of everything we need to know about radians. Right? So I'm thinking fraction of a semicircle. Fraction of a semicircle. So 30 degrees, well, let's think. 30 degrees is how much out of 180? It's 1/6. So this is going to be pi over 6 radians. Right? If a semicircle is 1 pi, let's see. Well, 30 is a sixth of that. So I've got to do a 6 on both sides. About 240. Well, let's think. 240, that's going to be more than just 1, right? Over 180. I've got 4/3. So 4 pi over 3. Right? Pretty neat, huh? What about 270? And some of them you might start to be able to picture just like we did with the unit circle. So 270 out of 180, and I got 3 halves. So that's 3 pi over 2. Right? And you might, for that one, maybe you can kind of start to picture it. If I go 270 degrees, I'm going to end up down here. Right? So I've got 1 half, 2 halves, 3 halves. I'm going to cover 3 halves of a circle before I get there. No, it won't let me write. Right? And then 4 halves. Oh, it's the 2 pi. How cool is that? Right? So 90 degrees would just be 1/2 pi. So cool. So cool. Okay? And then finally, our final thing we talked about was arc length, which is radius length times radian measure. And so this came after because we needed to know radians, right? There is a way to do arc length with degrees, and that's all, and that's all great and fun and dandy and all of that. But arc length with radians, like think about how, like radians take something that's angular and they make them linear for us, right? Like it's very concrete. So if I want to know the length of an arc, right, that portion of the circumference, that's why if you've just found a circle, that's why it's 2 pi r, because 2 pi radians times the radius is equal to the circumference, right? Like that is what the formula is telling us. So let's say we knew that this arc length right here is 15 pi, and the radius is 18. So I have S and I have 18. And I want to figure out theta, the radian measure. Well, I'm saying how many 18s? 18 times what is going to give me 15 pi? So how many times does this radius fit into 15 pi? Well, if I divide by 18, I'm going to actually leave the pi. I'm going to get, they're both divisible by 3, 5 pi over 6. Oh, well, I just found theta, 5 pi over 6. So 5 pi over 6 radians, 5 pi over 6 radius lengths fit into this, right? If I take 5 pi over 6 and I multiply it by 18, 18 of those are going to fit into that length. 5 pi over 6 is less than pi, right? 5/6 of pi, 5/6 of a semicircle. See if you can visually kind of start to picture what that is. And then this last one, let's say I wanted you to find the whole perimeter here, this like Pac-Man. I'm going to say this is the center of the circle. We know this length is 9. We know this length is 9. That's the radius. I need to figure out what's this whole thing. So the arc length is going to be the radius times, well, how many are going to fit into that? I'm telling you, 5.64 radius lengths. The number of radius lengths in this arc, right? So if I multiply them, if I say, well, 5.64 sets of 9, 5 times, I don't have my whole calculator wasn't even on. 9 times 5.64, 50.76. Whatever the units are, right? That's the length of this. So if I want to find the perimeter of this whole Pac-Man, 50.76 plus 9 plus 9. Make sure I pay attention to the question. So I got 68.76 units. Okay? Awesome. So to summarize, we just went over your circle vocab, some key vocab and new vocab and old vocab that you knew. Tangents, right? Taking a look at slope. We focused with it on a grid. I didn't do any example with Pythagorean theorem. And then we looked at some central and inscribed angles, some radians, and then finally close out with some arc lengths. So you guys have a task to make sure that you finish Delta Math. You also have a lot of extra resources posted as you prepare for your assessment on this topic. Actually, your last assessment in geometry this year. Super exciting. And this is stuff like this is a great thing to end with because this is going to come back up as you move forward to Algebra 2. So Keep working at this stuff. Come in and ask questions if you've got them. And thank you everyone for joining me.